Welcome everyone to this new talk of the NA-GROM seminar series. Today with us we have the honor of having Professor Grepl, and he will talk about reduced order model, predictive control for parametrized partial differential equations. So please, Professor Grepl, the floor is yours. Thank you.
Thank you. So first of all, thank you very much for the invitation, and I very much appreciate the opportunity to give a talk in the seminar series. The topic, as you just said, is reduced order model predictive control for parametrized PDEs. And before I start, I would like to acknowledge my collaborators. Here we go. First of all, my PhD student Saskia, who has been working on this topic over the last couple of years. So everything you see on model predictive control and reduced basis methods is based on her contribution and her work. And we'll see that we also require some results from optimal control. And this is basically contributions from my former PhD student, Mark Kercher, in collaboration with Karen Baroy. So let me start with the goal and motivation of our work. We would like, or we consider parametrized dynamical systems, and our goal is to control such systems so that they follow a desired system behavior. And if we write that more formally, then we can write it as follows, as you can see here on top. So for any parameter mu, we wish to find a control U in some control space capital U, such that the state Y governed by a parametrized parabolic partial differential equation satisfies a desired system behavior. And by desired system behavior, we mean that can be many things, but for example, we might be given a desired state YD, and we want the state to replicate that desired state YD. Or if our system itself is unstable, for example, we would like to stabilize the system towards the origin. And just to introduce some assumptions and notation here, we assume that our parameter is given by mu. The parameter domain is given by this calligraphic D, subset of RP. And we assume that the state is governed by a parabolic parametrized partial differential equation, which is written up here in weak formulation. I'm sure you're all familiar with weak formulation. So, for example, M is the mass term involving the time derivative, A is the stiffness term, and then the right-hand side, B involves the control. We assume that for now that M and A are cursive and continuous bilinear forms. We will actually later on relax the assumption on A being cursive. We only require A to be weakly cursive or satisfy a guarding inequality. And again, B is our continuous control operator. Some more assumptions, as is usual in the reduced basis community. We assume that the bilinear form A, which depends here on the parameter mu, is a finely parameter dependent, so which means that we can write the bilinear form A as a sum of parameter dependent functions, theta A, Q, and parameter independent bilinear forms. And this is important for the efficiency, or more precisely, the offline-online decomposition later on. Since the model predictive control framework is inherently time discrete, I will already introduce a discrete time approximation of our dynamical system up here. So, and from now on, I will then only work with a discrete time formulation. So I'll introduce a time grid Tk as k times tau. Tau is our time step size. And then we use our favorite, let's say, one-step method, for example, the theta method, to discretize the time derivative here. And then we end up in short notation that y, k, so y, state y at time tk in some appropriate space capital Y satisfies this formula down here. So we can write yk as, or compute yk from yk minus 1. So the solution at the previous time step, the control at time step k, and of course that also depends on mu. So this short-term notation is basically used for the time discrete version of our parametrized PDE up here. Now, if we want to control a dynamical systems, there are of course many options that we have. You can discretize the whole PDE, for example, also in space to obtain a system of ODEs. You can go to classic control theory and look up how to control ODEs. Not always the best idea for PDEs. So sometimes it's better to actually work with the PDE itself. And there are many approaches that have been proposed in the past. For example, there's the backstepping control, there are flatness-based approaches, and so on. And one option that is also commonly used is optimal control. And we have worked on optimal control in the past. So let me start with a short introduction of the optimal control formulation. In this setting, again, we wish to solve for any parameter mu in D. We want to minimize a cost functional jk, here the typical tracking type cost functional, which involves basically the deviation of the state y from the desired state yd over the time interval. So in the continuous formulation, we would have the integral over time. In the discrete setting, now we have the sum over all the time steps. We have one term which measures the deviation of the desired state from the desired state at the final time step. And we have another term which measures the control input, again, subject to our parameterized PDE being satisfied. Again, here yd is the desired state. Omega d is our observation subdomain. So it doesn't have to be the whole domain, it can just be a subdomain. And sigma 1, sigma 2, and lambda are the regularization parameters which allow us to tune the solution or the optimal control problem. And these will also serve later on in our setting as parameters that we want to vary so that we can basically tune them online. And as you can see here, I've written down the so-called finite horizon optimal control problem. So our sum doesn't go to infinity, but just to k. Whereas in the beginning, I said we would like to control our system for all time. Well, we could now theoretically let k go to infinity to obtain the infinite horizon control problem. But of course, the issue is that the solution of this control problem becomes more and more expensive as k grows. And also, if k goes to infinity, there's the issue that the solution may not be feasible anymore. So the cost grows, the solution becomes more and more complex, and you might not have a feasible solution anymore, or the solution might not be feasible anymore to obtain. Another option with the optimal control formulation, or another problem, is that it's inherently open loop. So you compute the control once and then apply it to the system. I will from now on assume, because it's also not clear from the setting here, that the optimal control problem has a solution, so that there exists a solution. And I also assume that the infinite horizon problem stabilizes the dynamical system. Okay. So as I said, the infinite horizon problem is very difficult, if not impossible, to solve. So the model predictive control framework, or the idea behind model predictive control, is basically to solve the infinite horizon problem by repeatedly solving finite horizon problems. And I want to just briefly introduce the idea based on a sketch. So assume now that we are here at time step tk. We have a solution y of tk, and we have a control. So this is the past control input here. This is the past state. And we have a certain desired state that we want to follow. First, of course, we forget about the past. And I just said that solving the infinite horizon problem might be infeasible. So what we do is we restrict our attention to only capital K time steps ahead, which is called the prediction horizon. And now we are basically again in the setting of a finite horizon problem. So we can set up a finite horizon optimal control problem over the prediction horizon capital K. And we can solve this and, for example, obtain the optimal control input U star. From U star, we can then theoretically also compute the optimal state Y of U star. And now the idea behind MPC is not to basically go ahead all the way up to time step tk plus capital K, and then restart the process, but only to apply the very first control, so the first step of our control sequence. So we define our MPC feedback law as kappa of y0. Y0 in this case is actually y of tk as U star 1. So just the first entry of our optimal control sequence. Well, once we do that, we can go one time step ahead to this state here, y of tk plus 1, if we apply this MPC feedback law. And then we move the time horizon by one step forward. That's why it's also called receding horizon control. And now we are again in the same setting as before. So again, we have a state and we have a desired state and we want to follow. And then we again solve a finite horizon optimal control problem over this prediction horizon. Now, of course, I just said, or I assumed that the infinite horizon problem stabilizes the original system. But now there are, of course, many questions that you could ask, like, for example, when does MPC actually stabilize the system? So if we restrict our attention just to a prediction horizon, does that still work? Does it still stabilize the original system? Another question is, how good is the performance of our MPC approach compared to the performance, let's say, of the infinite horizon solution? And another question is, I just said that the larger K, the more costly it becomes to solve the finite horizon problem. But of course, the larger K, we know if K goes to infinity, that the MPC will also stabilize the original system, because for K to infinity, we obtain the infinite horizon problem. But we would like, on the other hand, to be K as small as possible. So the question is, how long does this prediction horizon have to be such that the MPC framework is stable? And luckily for us, there's lots of work on MPC in the literature, and you can find answers to all these questions. For example, by people like Lars Grüne, James Rawling, David Main, and so you can find conditions on and answers to those questions. But what remains is that we basically have to solve a finite horizon PDE constrained optimal control problem repeatedly over this prediction horizon. And as you probably can imagine, we don't have a lot of time because we need to do this very fast as the horizon moves on over time. So we have we require a repeated solution of those optimal finite horizon optimal control problems. And there's obviously then, if you think of model predictive control for PDEs, a need for model order reduction. And there's quite some work on model order reduction with model predictive control. And just a few weeks ago, I think there was a talk by Stefan Volkwein, which is in a sense very similar in spirit to what I'm going to present today. So the outline, I will briefly talk about model predictive control, the definitions and stability result that we require. Then I will briefly recall some results for the finite horizon optimal control problem, and then combine the two for a reduced order model predictive control framework. So just some definitions from the MPC literature in a sense. We define, first of all, the running cost, or the so-called stage cost, which is basically the cost in one time step. So if I would go back now to the cost functional that you just saw, these are basically the terms that appear in the sums or under the integrals in the continuous formulation. So again, the deviation of y from the desired state in one time step and the cost of the control. And this is called, again, the running or the stage cost L. Then we can also define an infinite horizon cost function if we just let the sum k run to infinity, which is simply the sum over all our stage costs or running costs. And we can define an optimal value function for a given initial state y0. We define j infinity star as the infimum over all u in u of j infinity. Okay, this is basically what we would like to compare our MPC framework to. So this is the optimal solution in a sense. And I require one more notation. So given a feedback law kappa from y to u, we denote the associated solution by y kappa k. So this control kappa here appears as a subscript of y if we plug in this control kappa in our formulation. And we also denote the corresponding cost of if we plug this solution then in our cost functional, so the control and the solution, as j infinity of kappa. And now we can again formally write down our MPC frameworks. So at time step tk, given our current state y kappa of tk, we solve the finite horizon problem y jk. So with horizon capital K, with initial condition y0 of y kappa at tk. We obtain the optimal control sequence, which was just written in green. Our MPC feedback law contains only the first element of our sequence, so u k star 1. We compute the next state at time step tk plus 1. And then we basically go again to the beginning, move our horizon one step forward and keep going. For this, we can now also define the optimal value function of the finite horizon optimal control problem, which we denote by jk star. Okay. So enough definitions and notation. So I said the question is, when does MPC stabilize the system? And there are, if you look at the literature, there are two main options. One is to basically modify the optimal control problem to add terminal constraints and or costs. And by terminal constraints, we mean that, for example, you could add a constraint such that the state at the final time has to lie in a certain subset of the state. Now, if you require that, and then you require that for all of your control problems, recursively, then you obtain what is called recursive feasibility. And by basically modifying your optimal control problem that way, you can then show stability. This is not really done in practice because it's quite complicated and not clear how to choose those constraints. So there's another option, which is not using terminal constraints and or costs. And I will focus on this one here. And the very important result or idea is the following, the so-called relaxed dynamic programming inequality. So consider a feedback law kappa from y to u, the corresponding solution y kappa with initial condition y kappa 0 equals y0, and a function v tilde that satisfies the following relaxed dynamic programming inequality. So y tilde of y0 has to be greater than y tilde of y kappa 1, so 1 time step ahead, plus omega times the stage cost evaluated at y0 and kappa of y0. This has to be satisfied for some omega in 0, 1 and all y0 and y. And then we know that for all y, the following estimates holds. So the idea is basically to use our finite horizon optimal value function as a Lyapunov function of the system, which then allows you to show stability of the MPC feedback approach. Okay. What you do to do that is basically you choose your finite horizon optimal value function, or you choose v tilde as your finite horizon optimal value function. And this omega here, which appears here in the relaxed dynamic programming inequality, is the so-called suboptimality degree. And it varies between 0 and 1 and measures basically the performance of your MPC feedback law compared to the optimal feedback. So the optimal would be the infinite horizon feedback. And if omega is close to 1, you know that your MPC feedback is close to optimal. If omega of mu is close to 0, but greater than 0, obviously, you know that you have stability, but your feedback law is suboptimal. And if omega is less than 1, you cannot conclude on the stability. So the idea is now to choose V tilde equals JK star, so the finite horizon value function, and set kappa to be our MPC feedback law. Then what is basically given, assuming that our assumption on existence and so on are okay, what we need to then satisfy is the relaxed dynamic programming inequality. So this inequality, again, for the choice V tilde equals JK star, and our feedback, the MPC feedback law. So we need to satisfy this inequality. We know that if K goes to infinity, that the infinite horizon problem stabilizes the original system, and we obtain the optimal feedback. So obviously, omega actually depends on K, and as K goes to infinity, you can actually show that omega approaches 1. Okay? And if K is too small, turns out that omega is less than 1. So let me then rewrite our task as follows. Our task is find a prediction horizon capital K such that yk star at y0 is greater than yk star of yu star at 1. Again, Timmy plugged in those values, plus omega of the stage cost evaluated at y0 and u star 1. And we want this to be satisfied for some omega of mu greater than 0, omega min greater than 0. And if I plot now the suboptimality degree over k, here's a plot of actually some of the results that we'll see later on. You can see here's the prediction horizon. And as we increase the prediction horizon, the suboptimality degree is less than 0. So for k, say smaller or equal to 6, the MPC feedback law will not be stabilizing. And then for k min equals to 7 and greater, we see that the MPC feedback law will start to stabilize. So this way we can determine the so-called minimal stabilizing horizon along our closed loop MPC trajectory. Okay. One issue with that, of course, is that we have to evaluate this omega. And if you look at this, you have to basically evaluate 2 optimal control problems, not just the one to compute U star, but also a second one to evaluate this. And this is quite costly, again, thinking of PDEs or optimal PDE constrained optimal control problems. So the idea is now to basically incorporate our model order reduction here to make this evaluation more efficient. So let me put a small info on parameterized optimal control problems in here, because if you look at this, we will need to basically evaluate cost functional values, okay, which are here high dimensional, but we would like to replace them somehow by a reduced order quantity. And for that, we need some result on optimal control for PDEs with model order reduction. So let me go a little fast on this one, which is actually past work. And I don't want to confuse you now, because now I wrote down an elliptic problem here and not a parabolic problem anymore. The reason is simply that the notation is much shorter and much easier, and the results in the end carry over directly. So again, we have our cost functional measuring the deviation of the state and the control, and we have some parameterized PDE. The assumptions here I already mentioned. We again have our state Y governed by this parameterized PDE, and same assumptions as before. And if we want to solve this now, this parameterized optimal control problem, what we do is we use the Lagrangian approach. So we have our cost functional, we append the PDE constraint with the Lagrange multiplier P, and we obtain the first order necessary condition. In this case, again, it's elliptic, so we obtain our state equation, we obtain our adjoint equation and the optimality condition. In the parabolic context, you would obtain, obviously, the parabolic state equation, so forward in time, the adjoint state or adjoint equation, which runs backward in time, and again, the optimality condition, which connects the control U star with the adjoint variable P star. This is a large system that we have to solve in the finite element context. So we want to speed that up. And what we do is we introduce our model order reduction. So given our sample set of parameters mu, we introduced RB spaces, Yn containing solutions of the state and the adjoint at mu n. And depending on if we have a distributed control or scalar control, also reduced basis space for the control. We construct those spaces using the greedy sampling procedure, which is also quite well known, I think, by now. And then we can write down the reduced basis problem statement. So again, we want to solve for any mu, minimize the cost functional Jn. Now we replace basically y by yn, u by un. We want to, again, minimize the deviation of yn from yd plus a regularization term containing un, such that the RB approximation of our parametrized PDE is satisfied. We again obtain the KKT conditions, same as before, just everything on the reduced setting now. And our system now is of dimension only 5n, so not anymore dependent on the finite element dimension, but only on the reduced basis dimension. And thanks to our assumption on the affine decomposition of A and B and so on, we can evaluate this very efficiently using an offline-online decomposition. What we require, however, is a bound on the optimal control and cost. So our goal is to develop a posterior error bounds for the optimal control. So the error between U star, the truth or FE control, and the reduced basis control, and the cost functional J star and Jn star. And the bound on the control is actually just a means to an end, because what we really are interested in now in the MPC setting is a bound on the cost functional. And just recall, we just said that we need to satisfy this relaxed dynamic programming inequality where J star appears. And so this is a crucial ingredient now, because it lets us in the end replace this J star in the dynamic programming inequality by a Jn star, so our reduced order quantity. And including the error bound, then still make sure that it also holds for the full order system, okay? So we need these bounds which are rigorous and online efficient, and there are several options in the literature, and several groups have worked on this. I just want to basically briefly mention this alternative approach based on Brezzi. What we require are the residuals of the state equation, the adjoint, and the control. We need a positive lower bound on the coercivity constant of A. We need an upper bound on the continuity constant of our control operator B here, and also this constant CD. And then we can show the following. The details are actually not so important. We can obtain a bound for the optimal control. So the error between U star and UN star, our finite element or full order control, optimal control, and the reduced basis control is bounded by this error bound, which we can compute from these quantities C1 and C2. And C1 and C2 basically incorporate the dual norms of the residuals and the constants we just introduced. And if you are familiar with the reduced basis literature, then you see that we can, again, compute these dual norms offline, online efficient, okay? So we can evaluate this bound, again, using an offline, online decomposition. And in the online stage, the cost to evaluate this bound is independent, again, of our finite element dimension. It only depends on the RB dimension. And I mentioned more importantly, we also require this bound for our cost functional delta nj. And this is basically, again, computed from the bound for the control, the bound for the state, the bound for the adjoint, using the dual weighted residual approach. Okay, so now that we have our bound for the cost functional, and again, I mentioned this now here for the elliptic case, but in the parabolic case, the derivations are more or less analogous. So if you think of the time discrete formulation of your parabolic problem, you have an elliptic problem in every time step. So what you end up with is basically you end up with sums over the residuals on each time steps, okay, just approximately. But the idea behind the derivation is very similar. So let's go now back to model predictive control and combining that with the results that we just saw. So recall that we said we would like to find the smallest k. This is the smallest stabilizing horizon, so that we are as efficient as possible, but still stable, such that this relaxed dynamic programming inequality holds for some suboptimality degree omega of mu greater than 0. And we just saw if we increase k, then omega will, k goes to infinity, omega will tend to 1. But of course, we would like to, at the same time, keep k as small as possible, because the computational cost is important. And again, this requires 2 full order OCP solutions. Now, how can we go about combining our results on model reduction for finite horizon optimal control problems with a receding horizon idea? Well, option 1 is we could simply replace U star by UN star, which has been done. Basically, it's the obvious idea. It's been done many times in the past. So if I simply go to my relaxed dynamic programming inequality and simply replace U star by UN star, I obtain this. And now in blue, I basically write down everything that is efficiently computed. So it's a reduced order quantity. But if we look at that, well, then we can compute UN star efficiently from what we just saw. But we still need to evaluate JK star and J, those two basically optimal value functions. So this still requires 2 full order OCP solutions, although we can compute UN star efficiently. So that approach is not enough to basically guarantee stability of the closed loop system. And by closed loop system, I mean computing the MPC feedback law from the reduced order model, but plugging it into the full order model. Okay, so controlling the full order model with a reduced basis MPC feedback law. Option 2 would be, well, we could additionally replace those optimal value functions with our reduced order optimal value functions. And if we do that, well, that looks much better in a sense, because now we can actually compute everything efficiently. But the problem is we are basically deviating from what we wanted to show up here. If you do the analysis of this, you can actually go straight to the papers, let's say by Lars Grüne. And what you show in the end is you show that your reduced order MPC feedback law stabilizes the reduced order system. Okay? Basically, it directly holds what you just showed for the full order system, directly holds for the reduced order system. But again, this is not what we wanted to show. So we require no full order solution. But the problem is that we only guarantee stability of the reduced order system and not of the closed loop full order system. So that also doesn't work. So let's go back again, actually, to option 1 and look at this inequality again and think of that we just said, okay, we also have a bound on the optimal value function that we just derived from our OCP formulation. So what we do is basically we replace U by UN star as before, and we employ our bound on the optimal value function. So if we start now, sorry, with this jk star of y0, we know that this is lower bounded by jn k star, so our reduced basis, cost functional, optimal value function, minus the error bound. If I look at this one, this quantity up here, I know this is upper bounded by jn k star plus the error bound, of course, then also plus this term, which is greater than what we have here. So now if you look at this and you look at the inequality here in the middle, then you can see that we now have everything that we need. And in a sense, what we do is we consider like a worst case of the relaxed dynamic programming inequality by using our error bounds on the cost function. And from this middle inequality here, we can define a new suboptimality degree, omega. So we simply bring those two terms on the left-hand side and divide by L. And if we do this, we define or we obtain a reduced basis suboptimality degree, which contains, again, the value functions and the error bounds, in a sense, a worst case of the optimal value function. And then it's easy to show that if there exists a k, minimal stabilizing horizon, such that omega nk is greater than 0, then also the original suboptimality degree is in 0, 1, meaning that our reduced basis MPC feedback law stabilizes the original full order system. And this is basically it. So we require no full order solution. We guarantee stability of the full order system. Well, we do still require a projection of y0, the initial condition, which lives in the finite element space, onto our RB space yn, but that only costs O cal n if calligraphic n is the dimension of our FE space. So the RB scheme is then as follows. At time step tk, given our current state, we solve a finite horizon problem, an RB, important, reduced basis finite horizon problem, to obtain our reduced basis optimal control solution, un star k. We define the RB MPC feedback law, again, as the first element of the sequence. We solve another finite reduced basis finite horizon problem. We check whether our RB suboptimality degree is greater than 1. If yes, we have our stabilizing control. If not, we can increase the minimal stabilizing horizon by 1 and check again. So let me get to some results. The first one is a simple 1D reaction diffusion equation taken from a paper here by Altmüller and Grüne, who actually used the idea that I just mentioned originally for PDEs, just without model order reduction. We know that the uncontrolled equation is unstable for mu1 greater or equal to p square over 4. Our cost functional, again, we would like to stabilize y to 0. In this case, it's a stabilization problem. So we have the cost of y in the L2 norm plus the cost of the control. I mentioned before that in this case, actually, if you look at the bilinear form, it's only weakly coercive, but you can extend the ideas that we just saw also to that case. Our parameter is the parameter here appearing in front of the reaction term and the lambda appearing in the cost functional, and those are the discretization parameters. So let me show you some results for the average stabilizing horizon. So those are tests run over a sample parameter set for 2 different lambdas. Down here, you can see the minimal stabilizing horizon computed from the FE MPC approach that was, again, proposed before, basically in those papers. And here you can see the minimal stabilizing horizons of the RB approach, again, with guaranteed stability. And you can see, actually, in this case, they're very close even for small n. Problem is quite simple, and are very close to the finite element values. Again, if we plot the suboptimality degree, you can see it is less than 0 in the beginning, and then at one point becomes greater than 0. And at this point, we know that the feedback law starts to stabilize. And if we increase n, you can see that we basically approach the finite element suboptimality degree. Second problem, a little more complicated, is a welding process. Here, so the temperature is governed by a convection diffusion equation. We have here a welding torch, which runs over the workpiece, and we do a coordinate transformation to obtain a convection term in our model. So the torch is stationary, and we introduce an artificial velocity field. We have a diffusion term and the heat input from this welding torch, which is modeled by the Gaussian function. Our cost functional, in this case, we would like to basically control the heat input from the welding torch such that the temperature here at this point, basically halfway through the workpiece, is equal to the melting temperature. In this way, you can basically control the weld pool depth of the system, which is an important feature of the stability of your weld. So we would like to control or choose U such that Y, the state, the temperature in this region is close to 1. Our cost function, again, is the tracking type cost functional. Here are the parameters. Our input parameter, RMU1, the diffusivity, and again, the regularization parameter. And in this case, we also consider control constraints. I did not mention control constraints yet before, but you can basically extend. Another extension here is that we use a so-called multi-step approach. So compared to the standard approach, where you basically use only the first control in every horizon, in every MPC step, you use several controls and then move forward. Okay, so again, an extension which you can easily show. Here we can see the control and output. On top, you can see the controls. And here you can see, as I said, we want to control the output or the temperature to reach 1. This is the FE reference for us. This is the RB solutions for n equals 50 and n equals 82. You can see as we increase n, we get very close visually to the FE solution. Here are some average minimal stabilizing horizons. The lowest row here, again, are the finite element minimal stabilizing horizons. And you can see now a little better, because the problem is a little more complicated, that as we increase n, so as our reduced order model becomes more accurate, that the minimal stabilizing horizons basically match the finite element ones. And you can also see if our reduced order model is not accurate enough, then we have to choose a much larger stabilizing horizon, so very conservative, which has to do with the fact that our error bounds are simply not sharp enough. So since we consider worst case, we get much larger stabilizing horizons. But again, as our model becomes more accurate, we approach the FE one. And the gain, comparing now the speed up between RB, MPC, and FE, in this case is an order of 100. I mentioned before that omega is our suboptimality degree, and here we choose basically the minimal stabilizing horizon such that, which is the first K where omega becomes positive. And I said before that if omega is close to 1, you're close to the optimal, basically, feedback. So what you can also introduce is a so-called threshold on omega. So instead of just requiring omega to be greater than 0, you can require omega to be, for example, greater than 0.2, which makes your RB MPC feedback law closer, or brings it closer to the optimal one. And you can see it here. We did that here, that in the beginning, for this one, you can see still a slight wiggle here at the solution. Here you can see that we get well, flatter and flatter, or more and more smooth towards the optimal solution. And again, here's the finite element and the reduced basis solution. If you look at the average minimal stabilizing horizons, then you see that they are slightly larger now, of course, because we want our feedback law to be closer to the optimal. And if you think of the fact that our omega increases as k increases, so we of course require a slightly larger k, so a larger minimal stabilizing horizon to then obtain this threshold on omega. Here are some results on the constraint case, which I'm maybe going to skip because I want to spend maybe just a few more minutes on the nonlinear case. So the extension to nonlinear problems. The problem, of course, is that the DVR, so the dual-weighted residual method that we use for the cost function error bound, is not valid in the nonlinear case. So what can we do? Well, there are two options. We can linearize around the current state. We can then compute the RB-MPC feedback law that we just saw for the linearized model and apply to the full order nonlinear model, which guarantees, of course, closed loop stability, but only of the linearized full order model, not of the nonlinear full order model. The other option that we considered is an RB-EIM approximation of the nonlinear problem. So we compute the MPC feedback law from the nonlinear RB-EIM optimal control problem. And we choose k such that the suboptimality degree is positive. But if we do this approach here, so the second option, then we are in the setting that we basically show stability of, or that we can guarantee closed loop stability of the nonlinear RB-EIM approximation, because we again replaced our cost functional with a reduced order cost functional. Okay, important disclaimer that we cannot guarantee closed loop stability of the full order nonlinear system for either of those two approaches. Okay, that's still an open question basically. And some last results for the Schlögl model, well known also in 1D here. We know again that the uncontrolled equation is unstable for mu1 greater or equal to pi squared over 4. Our cost functional, we want to stabilize the system to yd equals 0. Our input parameter is mu1, so the parameter in front of the reaction term, and again the lambda appearing in our cost functional. And here is a sample solution of the uncontrolled system, so you can see if mu is larger than the pi square over 4, then the system becomes unstable, reaches an equilibrium here not equal to 0, and only for the smallest mu1 it actually goes to 0. And here are some results for the FE MPC and the linearized RB MPC for n equals 5. Again, for the different parameter values, the finite element MPC approach stabilizes, and our linearized RB MPC, you can see that the controls are a little smoother, but they also work for all parameters and stabilize the nonlinear system. Again, these are chosen such that, basically based on the theory that I just presented for the linearized case, such that the linearized model is provably stable. Okay, but we see that if we do this along the system trajectory and linearize, it also stabilizes, seems to stabilize the nonlinear system. These are results for the RB-EIM approach. So the second approach, we see that visually they're closer to the FE approach, but they also stabilize the system for all parameters considered. Here are, again, the minimal stabilizing horizons. On top in red, the FE ones. Here the linearized ones, and the lowest row is the RB-EIM ones. And we can see that the linearized ones are slightly more conservative than the RB-EIM. And this is again for actually the values of n and m that we just saw here in the plot. So for n equals 5 or nm equals 3, 4. But the speed up is considerable. So the linearized RB MPC versus the FE, the speed up is order 10 to the 4 to 10 to the 5. For the RB-EIM, the speed up is order of 10 to the 3. And the final result is, can we also stabilize the system through a stable equilibrium? So if we not come from the bottom and immediately try to stabilize to 0, but we actually come from the top and try to stabilize to 0, where we have to go through a stable equilibrium. And here again, results. MPC works for the FE, and now we need a few more basis functions, but the linearized and also the RBEIM approach both manage to stabilize the nonlinear system through the stable equilibrium. And with that, I want to, summary, too many M's, summarize and conclude. So we developed a reduced order approach for MPC of parametrized PDEs. Our MPC feedback control is efficiently computed from the ROM, and we can guarantee stability of the closed loop system, meaning the RB MPC feedback law applied to the full order system. So our reduced order control stabilizes the full order system. And we have this adaptive strategy for the minimal stabilizing horizon and extended those ideas, as I just showed you, to nonlinear problems. Well, to do, there is an extension. We are currently extending the ideas to distributed control problems. There are some robustness issues, which is called practical MPC, which we are looking at currently. And also, I mentioned that we still need to project the initial condition. So it's going to be interesting to look at output MPC or an observer design such that we can also avoid this initial projection in every MPC loop. And with that, here we are. With that, I want to thank you for your attention, and a small ad. We have an open PhD postdoc position, so if you know of anyone, or if anyone here is interested, please contact me. If you know of anyone who is interested, please let them know. Thank you very much.
Thank you. Thank you very much for this great talk. Now is question time. So from the audience, you know that you can unmute yourself and ask your question directly to Professor Grepl if you want.
I have a question.
Great.
Can you go back to the slide where you had the elliptic a posteriori error estimates?
Yeah.
Or where you introduced the 3 different techniques? And my question is now the following: you have 3 different techniques, so which one is the best, or in which situation is one of the best? Can you compare them and comment on that?
Yeah, a very good question. We looked at that in a previous paper, actually, at those 3 approaches. So the perturbation approach was based on a work by Freddy Drölsch and also used in the POD context by Stefan Volkwein. In their classic formulation, it actually requires still a full order solution, which we avoided, but it made the bound quite conservative. Okay, this is the perturbation approach. The BNB approach basically looks at the optimality system. Wait, let me see. Written down here, which you can write as a system of PDEs, which is then non-coercive, and you can use the BNB theory to obtain a bound for the triple. So not just for the state or the adjoint, but really for the triple state, adjoint, and control. And this alternative approach is, I said, based on Brezzi. So it's based on a posteriori error results for saddle point problems by Brezzi. And now, concerning your question, which one is the best? We looked at the behavior of these bounds. If I plot it here, of the control bound and the cost functional bound, depending on the regularization parameter lambda. And it turns out that as lambda becomes small, the perturbation bound deteriorates quite badly. The Banach-Netjes-Babushka bound deteriorates, I think, with 1 over lambda. And the best performance for us was this bound on Brezzi, which only basically deteriorates with 1 over square root of lambda, if I'm right. Okay. So all of those bounds basically deteriorate if lambda becomes very small. But the best performance that we observed so far for the problems that we looked at was this alternative approach. Okay. Again, this is limited to the problems that we looked at. the other advantage of this alternative approach is actually that if you look at the formulation, you require a lower bound on the coercivity constant, whereas if you do the BNB approach, which actually performed closest to the third approach, you require a lower bound on the inf sub constant of your optimality system. And computing this lower bound on the inf sub constant is really complicated and complex, okay, such that people usually don't do it and go other ways. In that setting, the alternative approach makes your life easier because it only requires a lower bound on the coercivity constant, which is a much easier problem, which you can usually obtain much simpler than a lower bound on an sub constant. Sorry, long answer to a short question, but I hope it answered your.
Yes, thanks a lot. It was very informative. Thank you.
Yeah.
The question, Ryan, please.
Right. Okay. So first of all, this was a wonderful talk, Martin. Thank you. Excellent talk.
Thank you.
I mean, it was very clear. I really enjoyed it. And in fact, I'm teaching a rounds for fluids course today, and I'm gonna tell students to take a look at the interesting control to take a look. It was a very clear presentation. Thank you. Very nice.
Thank you.
So my question was a little bit about, so it's a naive question, but it's about what you said towards the end. So I think that the whole procedure was beautifully, it's certifiable. So the method is certifiable. It can guarantee, the error bounds for linear problems, coercive problems. When you move to the nonlinear case, this becomes a little bit more complicated. Now, what I was gonna say is, so for somebody like me who's interested in fluids, I mean, I would say that probably extending this to flow past the cylinder, like Navier-Stokes, I think that this makes sense. But I'm wondering if you want to extend this to more complicated. It's a naive, it's a general question. So, like, think about turbulent flows, so convection dominated, under resolved, so really hard problems. What's your take? What's your thinking? So is it reasonable to assume to aim for certifiable bounds, or maybe something like POD or some sort of for which you cannot guarantee these bounds, or not avoiding these bounds? Would this be something maybe a bit more practical in this type of realistic situation? So it's a general question, and it's, I'm just trying to understand what you're thinking about this.
Yeah, that's a good question. Well, so the what is really crucial again are those bounds on the cost function that we require. And as you said, if we want the approach or the MPC approach to be certifiable, we need this bound here to be certifiable. Of course, it doesn't really matter where your reduced basis comes from. You can do a POD basis, you can do a balanced truncation basis. I mean, the bound still holds. Okay, that's fine. But of course, if you now go towards, let's say, convection-dominated problems, then we know that just from the forward problem itself, usually those bounds deteriorate. So just for the forward problem itself, it will already deteriorate, let alone for the optimal control formulation. In our setting, the bounds actually on the cost function are already quite conservative, but it still works fine. Although the effectivities are actually quite large, okay? Which I think is due to the fact that we have those really small horizons that we are looking into. So even if your bound deteriorates for large K, usually the K is quite small, so we are fine with a large effectivity. That's our observation so far. I think it all depends how the literature and how the work will be on error bounds or on certifiable reduced order models for the forward problem itself. If there are ideas already so far in the future, which guarantee or which give you a certifiable bound for the forward problem, then I'm hopeful that you can use those also in this setting, and in the end maybe get a certifiable MPC framework for those problems. But if you don't even have a certifiable bound for the forward problem, then yeah, you're a little bit in trouble for the MPC framework. I hope that answered your question. It was not maybe not very satisfying. Yeah.
No, it was very good and very, very clear. Thank you. I really feel excellent talk once again. Thank you, Martin.
Are there other questions?
Yeah, I might ask a curiosity on, I think it was slide 23. So a few slides after this. Yes, so this picture that you have at the bottom. So if I understand correctly, the figure there is showing omega. The curves there represent omega, and you're looking for the value of k in which this curve becomes positive.
Exactly.
But there you have a line associated to n equal to 5, in which the curve is at the beginning negative, then positive, and then becomes negative again. Is that a side effect of having a very small reduced basis, or could a configuration like that one also happen with finite elements, for instance?
I think you are actually not guaranteed that, or under certain assumptions, there's an assumption which is called exponential controllability. Then you can actually show that omega tends to 1 as k tends to infinity. But I don't think we would need an expert now on this, like Lars Grüne. I don't think you are guaranteed that this converges as uniform. Okay. In this setting, I think it's that it again goes bad is due to the fact that our reduced order model is not accurate enough. But that's only an assumption, so we couldn't prove that at this point. I can't really give you a good qualitative answer why again it seems to become unstable at this value. Yeah.
Okay, great. Thank you.
What is important for us was that it actually seems to converge to the FE as we increase n.
Yes.
What it does for the smaller ones, is always with reduced order models always sometimes a surprise package, I think, as you know.
Great, thank you.
Yeah.
So it seems that there are no other questions for Professor Grepl. So I think that we can thank him again for the beautiful talk he gave. And we see each other next Tuesday with the next NA-GROM seminar. Thank you. Thank you very much.
Thank you very much. Bye-bye.
Thank you, Martin. Bye.
Bye.
Thank you. Bye.